Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is the first video in a new series on number theory that I'm doing. And this video is about linear Diophantine equations. I'll explain what those are in a minute. Anyway, let's begin. So, what is a linear Diophantine equation? I guess first I have to define what a Diophantine equation is. And by the way, number theory is all about solving Diophantine equations or systems of Diophantine equations. So a Diophantine equation is a polynomial equation. That means it's an equation in terms that are like powers of its variables. So it's a polynomial equation whose solutions are restricted to integers. That's all it is. So and then they're named after a Greek mathematician Diophantus who lived in the third century A.D. He was the first mathematician we know of to consider these equations. That's why they have his name, Diophantine equations. And a linear Diophantine equation is that's the simplest type of Diophantine equation. That's an equation where the equation is first degree. So that means it's just a linear equation. Linear means degree 1. It means that all variables are just the first power of that variable. So if it's two variables, a two-variable linear equation just has the form ax plus by equals c, which they write on the bottom of the slide. And these are the ones we're going to continue. I'm going to consider today. Actually, you can have linear Diophantine equations of an arbitrary number of variables. Um, but I'm just going to consider two variable Diophantine equation. So that's the simplest type of Diophantine equation. And you probably learned in high school that in general, in order to solve a system of equations, you have to have the same number of equations as unknowns. And here we only have one equation and two unknowns. So you might think that this linear Diophantine equation is unsolvable or it has infinitely many solutions. Well, it's true that it has infinitely many solutions, but remember, don't forget the restriction we're making, that we're only considering integer solutions. So x and y are required to be integers, and we would like to be able to characterize all pairs of integers x comma y that satisfy this equation for given a, b, and c. These are just arbitrary given integers where a and b are not both 0, because then that would be trivial. But anyway, how do we do this? Well, there is a method, and here's the method. So there's 5 steps involved, and the first thing you should do is compute the greatest common divisor, usually abbreviated as GCD, of uh, of your first two numbers, a and b, the coefficients of x and y. So you do that first, and then you want to check whether this greatest common divisor divides the c. And if it doesn't, then there's no solutions. There's no solutions in integers. It turns out, if b does not divide the constant term, that's pretty easy to prove. So that takes care of that case. But if it does divide C, the third step says you can simplify this Diophantine equation by dividing all the coefficients by D, by the greatest common divisor. Then you get a new Diophantine equation, which I wrote as A prime x plus B prime y equals C prime. This is a simple, this has the same solutions because all we did was divide both sides of the equation by the same number D. And that doesn't affect x and y. So x and y, it has the same solutions as the original equation. It's just simplified. Because now a and b are what are called, a prime and b prime are what are called coprime, or sometimes people say relatively prime. That means that their GCD is 1. They don't share a non-trivial common divisor. So now, step 4 is we need to find new integers, which we call u and v, such that a prime u plus v prime v equals 1. And this is, you can kind of think of this as a kind of a basis solution. I mean, you can build up from this, but I'll get to that later. And sometimes you can do step 4 by inspection. The examples I'm going to give today, you can actually find a prime. you can find u and v by inspection. Sometimes it's not hard to do that, especially if a prime and b prime are small. But if a prime and b prime are very big, you have to use another method called the extended Euclidean algorithm, which is a pretty complicated algorithm. I'm going to explain that in a future video, maybe in the next video. There's also a nice algorithm for just computing the GCD. It's called just the regular Euclidean algorithm. So step one, sometimes it's not so obvious to compute the GCD of two integers. Sometimes you have to use what's called a Euclidean algorithm to do part one, and then you can do an extended Euclidean algorithm to do part four. And then once you've done that, once you've found these numbers u and v, then it's pretty easy to write. You can just write down what the general solution is. So step five says the general solution looks like this. X equals u times c prime. We already calculated u. So u plus c prime plus k times b prime. Where now k is just an arbitrary integer. K can be any integer you want. And the simplest value of k to choose is 0. But it can be any other integer as well. That'll also give you a solution. And similarly, y is equal to v times c prime minus k times a prime. And it's not too hard to check that this is it is indeed a solution to your original Diophantine equation. I'm not going to do that. You can check it yourself. But the algebra works, and you'll find that it does. This pair x comma y does satisfy the original Diophantine equation, ax plus by equals c. Anyway, so that's how you solve it. And I'll give you some examples. So here's the first example. Suppose our Diophantine equation is 3x plus 4y equals 5. So now the first thing we do is we compute the GCD of the x and y coefficients, 3 and 4, and that's 1. It's pretty easy to see that 3 and 4 don't share a non-trivial common factor. So the GCD is 1. And now step 2 becomes trivial since d is 1, obviously it divides c, because 1 divides any integer. So we're okay. We have solutions. And then for step 3, again, since d is 1, we really don't have to change a prime. A prime is just equal to a because we're dividing by 1. So a prime is 3, like a was. B prime is 4, like b was. And c prime is 5. So we didn't change anything. And then again, in step 4, we do inspection. So we want to find a solution to the equation 3u plus 4v equals 1. And it's pretty easy to see that if we set u equal to -1 and v equal 1, this works. So now we found u and v. And so we didn't have to use the extended Euclidean algorithm. That was nice. And then for step 5, we just complete the solution. So completing the recipe I gave on the last slide, uc prime, that's going to be -1 times 5. That's -5. And k times b prime in this case is 4, so that gives you 4k. So that gives you -5 plus 4k. And then for y, it's the same thing. Y, remember that one was vc prime, v is 1. So we have 1 times 5, that's going to give 5. And you're going to get minus k times 3, so minus 3k, 5 minus 3k. That's how you get the last line. And you can check that these indeed are solutions. And I actually graphed them. It's kind of nice to look at a graph of the solutions to a linear Diophantine equation. It's always a discrete set of points. It's always a discrete set of infinitely many points along the line. So if we were allowing x and y to be arbitrary real numbers, we would get this entire line. And I'm sure you guys learned in when you were learning algebra that the graph of a linear equation like 3x plus 4y equals 5 is going to be a line. That is just a line. And then you get these discrete set of points because we're only allowing x and y to be integers. So that's what the graph looks like, and that's what the solutions look like. Nice. So I'll do a couple more examples. Example 2. Suppose instead of a equals 3, we did a equals 2. So now our equation looks like 2x plus 4y equals 5. Well, now if we calculate the GCD of 2 and 4, we get 2. And because 2 doesn't divide the 5, um, C equals 5, I should have said. There's no solutions. And you can kind of see that by inspection. I mean, look at the left side of this equation. 2x plus 4y, obviously that's even because 2 and 4 are both even. So whatever's on the left side of this equation is going to be even, but 5 is odd. So that's kind of a proof at a glance that there's no integer solutions to this equation. So what about example 3? This is probably the hardest one I'm going to give you. What if our equation looks like 27x minus 18y equals 63? Well, let's just go through the procedure again. First thing we do is we calculate the GCD of the coefficients of x and y. In this case, that's 9. 9 is the greatest common factor of 27 and minus 18. So now we check whether 9 divides C, which is 63, and it does. 63 is 9 times 7. So the third thing we do is we divide all our coefficients by 9. So we're going to get A prime equals 3, B prime equals -2, and C prime equals 7. So in other words, our equation is equivalent to the equation 3x minus 2y equals 7. Um, and now, again, we can by inspection find a solution, u and v. It turns out that u equals 1 and v equals 2 will work. 3 times 1 minus 2 times 2. Actually, I think I did this backwards. Yeah, that's actually going to be minus 1. So I made a mistake here. I think u should be -1 and v should be -2. Um, but anyway, the general solution you'll get will look like this. Um, x equals 2k minus 7 and y equals 3k minus 14. I'm pretty sure that's correct. I checked it. You can check yourself. I mean, let's just do a sanity check here. K equals 0 is obviously an easy case to check. So x is minus 7 and y is minus 14. Let's see if that works. 2 times minus 7, or no, 20, let's do the simplified one. 3 times minus 7 is minus 21, and 2 times minus 14 is, or minus 2 times 1 is 14 is plus 28. That is indeed equal to 7. Minus 21 plus 28 is 7, so this works. And you can check that it works for other values of k as well. So anyway, that's how to solve linear Diophantine equations in two variables. And that concludes my video for today. So thank you for watching. Long live math, and I'll see you next time.